Oh, here we go into something huge. We are going into Riemann and trapezoidal approximations. So what we're going to learn now for a large part of the remainder of this lesson is how to approximate the area between a curve that is not what I call a nice geometric curve. So in a previous video, I showed you how we could make a nice rectangle, find the area between a horizontal line and the curve. This is far from horizontal. We don't have a nice formula that will give us the exact area between f of x and the x-axis. So what I'm going to teach you about is the very simple Riemann sum approximations in this video. So we're told to find or use a left Riemann sum. Now Riemann's just the name of this great mathematician who came up with this ability here. So we're going to use a left Riemann sum with 4 equal subintervals to approximate the area between f of x equals root x, the x-axis, and the interval 0 to 4. So 0 to 4 would be like start here and then end there. So we're talking about this area right in here, that space. Okay, how do we do this? Well, if we want 4 subintervals, so the overall interval is 0 to 4, so subintervals would be smaller parts. And that's where we enter in this whole idea, this formal ideas of this thing, which is delta x. And a Riemann sum, all that it is adding up rectangles. That's it. That's all that it is. So in all this notation, what is A, what is B? Well, A is always the start of your interval, and B is always the end x value in your interval. So A in this case is 0, B is 4. Delta x would actually also be known as the width of the rectangles we're going to use. So the width of rectangles, or the base. So the width of the rectangles. So to get the width of the rectangles, we need to know how many subintervals there are. That would be the n value. So you're going to sometimes see in math class delta x equals b minus a over n. Essentially what this is saying is how wide is the overall width? Well, that would be your ending x value minus your starting x value. 4 minus 0 gives you the overall width of 4. Then we're going to cut that interval into 4 equal parts. So n in this case is 4. That's the number of subintervals. So it makes sense that the change in x, the width of each rectangle, would be the overall width divided by the number of equal cuts we're going to make. 4 over 4, which is equal to 1. So in this case, delta x is 1. Okay, so in general, how does this work? Well, let's actually draw in a rectangle. Let's talk about what it means to have a left sum, and then we'll go over a right sum and then midpoint. So a left sum very simply means let's cut this into intervals and look at the left part of each interval. So our intervals are divided into 4 parts: 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And the reason why I know that's cut that way is because, again, 4 subintervals between 0 to 4, which would be 4 minus 0 over 4, which gives me 1. That's it. It's like you're cutting a loaf of bread into 4 equal parts. And if it's a width of 4, then each width of that loaf of bread is going to be an inch, if you will. So now we need to find the heights of rectangles on each interval. So you focus on each part. Well, this one's kind of weird, but on the interval from 0 to 1, the leftmost point, left, is going to be at 0. So that's going to be right here. Well, the heights of these rectangles are determined by the curve. The height at 0 is just 0, so we actually get a rectangle that has no height at all. That one might be a little confusing, but let's keep going here and draw a picture. Now look at the interval from 1 to 2. I'm going to do that in a different color. From 1 to 2, our left endpoint from 1 to 2 would be at 1. And so that's going to be a height determined by the y value at 1, right there. And you complete your rectangle until you get over to 2, where the interval ends. That's it. That's not so bad. And then we go on from there. We're going to do a left endpoint now at 2. Oh, there we go. Okay, so that stretches up here all the way there. And we write that rectangle all the way over till we get to 3. We stop there because that's the end of that subinterval. And finally, we have one more rectangle to go. The left endpoint on the interval from 3 to 4 would be at 3. So visually, this is what it looks like. All right, so then how do we find the areas of these rectangles? To approximate the area, the whole thing, we're going to add the areas of the rectangles. Well, notice this. Notice that the height of each rectangle is going to be f of whatever that value is. So for instance, the height of this rectangle is f of 0. The height of this rectangle right here is f of 1. The height of this rectangle right here, that one right there, is f of 2. And the final height, f of 3. Oh. And then the widths of the rectangles in this case are each 1, but overall it's delta x. That's the width. So if you're thinking overall, what you're doing to find the area of a rectangle is you're multiplying the base times the height. So in this case, that would be f of 0 times delta x, just doing it out formally, plus f of 1, this height times delta x, nice, plus f of 2 times delta x. That would be the height of the third rectangle, right, times the base, which is delta x, plus f of 3, not bad, times delta x. If we add up the areas of these rectangles, we've added up 4 base times heights. Well, what's f of 0? How do we find that? The function is the square root of x. We know that. So that would be the square root of 0 times delta x is 1, plus the square root of 1 times 1, that's delta x, plus the square root of 2 times 1, delta x is 1 the whole time, plus the square root of 3 times 1. Now you might have noticed that we could have written all of this out and factored out the 1, right, from everything. So now we just plug it into our calculator. That's going to be 0 plus 1, and then you just do the square root of 2, which is going to be about 1.414, plus the square root of 3, which is about 1.732. And when we add that up, we get ourselves 4.146. So it's about 4.146. So that's the approximate area here using what is called a left Riemann sum. That's it. That's all there is to it. We're adding up the area of each rectangle. And I have here, what's the area of one rectangle in general? That would be f of whatever x value you have times delta x. And again, always from the left-hand side. Okay, let's continue this. And I want to couple this with the right Riemann sum. And then we'll end the video there and we'll go into, there's one other kind of Riemann sum. So that's it. That's the left-hand Riemann sum. It's not so bad. Use a right Riemann sum, same curve, with 4 equal subintervals to approximate that same area from 0 to 4. Okay, so again, we're still looking at this area here from 0 to 4. Overall, what we know is that delta x has not changed, right? That again is b minus a over n, where n is the number of subintervals. That's 4 in this case. The endpoint of b is 4, and a is 0. And so overall, the width is 1. If you got 4 rectangles over a span of 4, each one is 1. So again, I like to put in little tick marks to show my subintervals. All right, now if you're not given the graph, you're going to eventually be able to do this mentally, just with this thing right here. Now we're doing a right Riemann sum, so now the heights come from the right side of each subinterval. It's no different what we do, except the heights come from this side. So from 0 to 1, the rightmost endpoint would be x equals 1. And again, the width is still over 0 to 1. Now we go to the second subinterval from 1 to 2. What's the rightmost endpoint? Well, that's going to be here. And you connect that all the way over until you get to 1, because that's the interval from 1 to 2. And here, rightmost endpoint from 2 to 3 is going to be, ooh, nice. It's going to be a height at f of 3. And then last but not least, 3 to 4, the rightmost endpoint occurs here at 4. Not bad. So now all we have to do is find the area of each rectangle. Remember, the area of any rectangle is f of the rectangle at the x value where we had the height go up, and it's not equals, I don't know why I put that there, times delta x. Delta x is the width. All right, so let's do this out without now writing all over this thing. So the first rectangle has a width of 1 and a height of f of 1 right here, right? That's the point right there, f of 1. So our first rectangle is f of 1, there's our height, and the width is 1. So there's the area of the first rectangle, plus the second rectangle, f of 2 times 1. Again, that would be delta x, so f of 2 times 1. And we could have, I'll show you, we could have factored out the 1. 2 to 3 is a width of 1, f of 3 is the height. Oh man, it's sweet. It's so simple, the geometry. So simple. Then the right-hand endpoint, f of 4 times 1. It helps to see it visually. You don't have to graph it out, but it certainly helps to see it. So now we just plug this into our function. So we get the square root of 1 times 1, plus the square root of 2 times 1, plus enter 3 into the function, right? Because the function gives you the height of the rectangle. Root 3 times 1 plus root 4 times 1. And what's that value going to be? Well, we plug in everything into our calculator, and we end up with 6.146. Now that obviously is an overshot, right? Because the area we're finding is the area here, all of that, right? So you've actually found all of the area and then some. Whereas in the last one that we just did, we only found the area underneath the curve here, but we left out all of this space. So I asked a question. And the question I ask at the bottom here is, what two values must the exact value be between? Well, we know that the undershot was 4.146. So the area will not be less than that. And the overshot, this was a clear overshot, was 6.146. So I don't know what the exact area is. Not yet. We'll be able to find that down the road, but I know it falls between the left and right Riemann sums. More on what's an over and an under approximation down the road, but for now, we'll end it here. See you in the next video, a midpoint Riemann sum and a trapezoidal approximation. I can't wait. Peace.